appreciate being able to be here and to support the chapters in the education for building decarbonization. Typically we're providing our Energy Code ACE sessions to really give you a deep dive into what's in the Energy Code and to help support your learning around incorporating the Energy Code into your projects and your practice. Today we're taking a little bit of a step back and looking at some of the broader issues and questions around the direction that the state is headed with these various policies. And really this course, which I'll start sharing right now. So let me, title slide, is that
Yes,
right?
we can.
Excellent. Great. So yeah, this talk is really designed to try to help answer common questions that come up around this transition that we're at the leading edge of in the architecture profession, and really to try to help provide you with information and insights that will help you respond to questions that your clients have as you're incorporating this into your projects increasingly. So you have the learning objectives, of course, from when you registered, so we don't have to go over those, and I've just kind of given you them in a nutshell. Quick little overview of the typical technologies that you'll see in an electrified building. A lot of the information in the presentation today stems from residential, but the concepts are broadly applicable in most cases to most commercial uses as well. And we'll hit on some of that as we go through, but just again, some of the key technologies, of course, heat pumps, electric cooktops, primarily induction, electric vehicles, heat pump, water heaters, as well as space heating, and then the other kinds of enabling technologies like solar, batteries, and the smart panels and other controls that help all this stuff work together. So why don't we go ahead and jump into some of these kind of common questions that come up. Things we hear all the time when we're talking about this. So yeah, we were always told it was better to burn gas on site than at a power plant. Is this true? Was this true at one point? Is it still true? What do you guys think? I can't see the chat, so I won't see your responses, but if anyone wants to verbalize, that's perfectly fine too. So at one point, that was fairly true. When we had very little renewable on the grid, it was much more efficient to burn, gas on site in an appliance than to, burn it at a power plant with all the losses that go with that, as well as the transmission losses just to run electric resistance. That's changed quite a bit. Two main factors that we'll go into in detail, but the increasing penetration of renewables on the grid, it's just a waypoint at this point on our way to completely carbon-free electricity targeted by the state by 2045. We're already in SCE's portfolio, 43% carbon neutral, and it's over 50% statewide. You can see the breakdown here. And these power content labels give you that, the kind of the breakdown. These are available from the CPUC's website. They have them available for every year. I think the 2022 might be available now. So I could probably update this and you'd see about a 2% roughly increase. That's kind of where the pace is in terms of increasing the penetration of renewables. But in addition to the traditional renewables like solar and wind, there's some other sources of carbon neutral power on the grid, such as we still draw statewide from Diablo Canyon, which is nuclear, but still considered a non-emitting resource. So this is a helpful graph or table to really understand what the current mix is, how it's trending, and where it's going. So you can see that we really are on a pathway to carbon neutrality. So it really changes the calculus in terms of, the more that you're powering from that carbon neutral electricity, the lower your emissions are going to be overall. And that's, I should note, not even considering on-site solar. That's all considered behind the meter. Those charts in terms of percentage is entirely based on what retail sales are delivered. So that's all utility side. So the true carbon neutrality numbers in terms of power usage in California overall for electricity are actually higher as a percentage if you factor that in, but it can be hard to quantify exactly how much power is being generated by rooftop solar at every site throughout the state. One of the key concepts that if you come away with only one thing from this whole presentation, I want it to maybe be this, and that is that, currently in our kind of fossil dominated energy economy, again, we're transitioning from it gradually, but if this is called a Sankey diagram. The Department of Energy puts these out. They do breakdowns by state. This is the national breakdown of energy flows throughout the U.S. So, in California, our renewable percentages are higher. But you can see kind of all the different sources on the left-hand side, and what not percentage, but how many quads, that's quadrillion BTUs, British thermal units of energy, that we derive from each of these sources. You can see we're primarily a fossil-based economy. It's 80% plus nationwide, natural gas, coal, petroleum, and that's going into all end uses. You see kind of to the right middle, kind of the different sectors: residential, commercial, industrial, and transportation, and which fuel types go to each of those. The really stark thing that you notice when you look at this diagram is that light gray box, that of all the energy input, almost 100 quadrillion BTUs of energy input, we basically reject 2/3 of that into the atmosphere as waste heat. So imagine buying your groceries, and you pay 3 times as much, and you just put 2/3 of what you're paying for your groceries into the shredder before you can leave the store. What we're really concerned about is that dark gray box. What we really want out of our energy economy are those energy services. That's useful work being done by the energy inputs that we have. So, electrification gets at both of these boxes, and we'll talk about the efficiencies of the different equipment and why that is. But, one, we don't have all that rejected energy going out of power plant stacks, flues from furnaces and water heaters and other gas burning equipment, and tailpipes, right? So that the more we can reduce that box, and also heat pumps, we'll talk about, we can reduce that energy services need by using heat pumps, which we'll go into in a couple of slides here. But that's a key concept, is that it's not that we're trying to replace everything on the left, because the more we can shrink what's on that far right-hand side, the less we need inputs on that left-hand side. And transitioning to renewables really helps us to reduce the size of the boxes on the right, which reduces the size of the boxes on the left that need to serve that. So hopefully that all made sense. So how do we achieve that? So we've talked a bit in previous sessions in our code breakers about the really significant efficiencies of heat pumps. Heat pumps are effectively 300% efficient. You get more output than you do input, because it's not actually converting a fuel, it's just moving heat from one place to another. Heat pumps are reversible, so you can use them for both heating and cooling, just like a standard air conditioner. And you compare that to a gas furnace or water heater, which, if you have a really efficient unit, that's a high efficiency condensing model, they top out about 95%, give or take. So you're really getting 3 times the bang for your buck for that energy input with a heat pump. And again, that goes to that dark gray box, the energy services piece we talked about. The parts of that energy services that are space heating, we can reduce that just by going to heat pumps, even if we don't change the fuel that feeds it. Even if we don't get at the renewables piece, just using heat pumps helps us in terms of reducing that box. Gas versus electric stoves. Gas cooktops are approximately 40% overall efficient. That means 60% of their energy is just going out into the space around it. It's making the kitchen hotter. It's that whole, kind of phrase you hear, if you can't stand the heat, get out of the kitchen. Well, induction cooktops are going to make those kitchens less hot. That means less ventilation requirements, less air conditioning requirements, less heat stress in commercial kitchens for the chefs. So it's a significant health and safety as well as a efficiency opportunity. Electric resistance cooktops, they get up to about 70 to 75% efficient. That's your kind of standard resistance, but like more of a smooth top, not that trying to avoid the exposed coil as much as possible. And then the induction cooktops, that's where we really get into those high efficiencies, where it induces that magnetic field into the pan. And again, we've talked in previous sessions about some of the technology, and we'll do a little bit more of an overview as we get into that section of the presentation today, but just understanding that it's more than twice as efficient, so your energy need gets reduced significantly. Relative efficiencies of gas versus electric cars. Again, that tailpipe, you're losing 68 to 72% of the energy in exhaust heat, just the conversion of the fuel, friction, etc. Your actual energy that the wheels see in terms of direct drive that actually moves the car forward is only about 16 to 25%. In an electric vehicle where you have direct electricity driving a motor without the conversion losses, and you have recovery through regenerative braking, you can see 87 to 91% efficiency. So again, just using that fuel much more efficiently without the combustion and without all the heat losses.
Hey, Dave.
Yes.
This is Jeff. There's a couple questions in chat. I thought I'd ask now because it's actually has to do with
absolutely.
The first one is, how about tankless water heater?
Tankless water heaters, so gas versus electric, is that the question? Or so a gas tankless is roughly in that 95+% if it's a condensing type percentage of efficiency. But if you're converting a fuel, whether that's electric resistance or it's burning gas or burning fuel oil, whatever, the maximum efficiency you can ever get with that is 100%. And you're always going to have some losses, minimum 2 to 5% pretty much. Or more depending on how efficient the equipment is, but appliance standards are going to keep that relatively to a minimum. Again, the efficiency with heat pumps, because you're not converting that fuel, you're using electricity to use the compression, the vapor compression refrigeration cycle to move a fluid around that just moves heat from one place to another. So you're in a cooling case, absorbing heat from inside your house into that refrigerant, sending it outside to the condenser coil. You are, compressing that fluid, and then you're blowing a fan over it to reject the heat to the outside. That's why when you go out to your outdoor unit, you put your hands over it while it's running, you can feel that hot air blowing off of it, right? So it's just like a sponge, absorbing and squeezing it out, that energy.
Okay, thank you. Next question, we have one other one. Have there been studies quantifying the heat differences and heat stress differences for gas versus electric kitchens? Seems it should be significant and easy to do, but I haven't seen any.
Yeah, I'm not sure if I have any off the top of my head. I know that some studies have been done. There's a company called Forward Dining Solutions. Chef Chris Galarza is one of the most prominent national advocates for induction cooking in commercial applications. And he has a lot of resources on his website that you can look into. And he tells a lot of anecdotes as well, just from his experience as a chef. But in terms of the actual studies, I'm not sure off the top of my head, but that's where I would start looking.
Okay, thank you. And that's all we have right now.
Okay, great. So just again, automobile efficiency, and we'll see this when we get to the cost, that this reflects there as well. Just significantly more efficient, about three times plus. In addition to the energy efficiency benefits, it's worth noting that gas use in buildings contributes 8 times more air pollution via nitrous oxide emissions than all of California's power plants. If you think about all those millions of distributed appliances and pieces of equipment through all of our buildings statewide versus the kind of concentrated sources you have at the gas power plants, that's, based on NRDC's data, it's 8 times more impactful. And of course, those are right there in our communities. A study by UCLA estimated that replacing gas with electric appliances would prevent about 350 premature deaths each year in California and produce 3.5 billion in annual health benefits from cleaner air. And that's available from UCLA, that full study. All right, so let's move on to the next question we get sometimes is that, yeah, we're gonna electrify and we're gonna add all these heat pumps, but they're gonna have a lot more refrigerants then. What's the significance of the refrigerants in terms of a greenhouse gas impact? So what do you guys think? Are refrigerants a big deal? Do they outweigh all the other carbon benefits? So factoring in refrigerants, we still see a significant reduction over time. Even today, it's roughly 45% a all electric versus a mixed fuel home drawing from standard grid power is going to see a 45% overall reduction in terms of GHG emissions. And that factors in that kind of dashed line that you can see with the hatched pattern that shows the estimated contribution from refrigerants. And you'll notice that the refrigerant leakage is going to go down over time as EPA regulations that have been proposed go into effect that phase out the worst performing refrigerants as far as the global warming potential. So R410A is slated for phase out very quickly. I can't think off the top of my head what the schedule is, but it's in the near term. So that impact is going to decrease over time. But even factoring in today's refrigerants, you still have a relative halving of carbon emissions by going to an all-electric home versus mixed fuel, and that'll be over 80% based on 2050 projections of what the grid's going to be like and what the composition of refrigerants will be at that time. Okay, what about cost? We sometimes hear people say that they're concerned it's going to be more expensive to run their house on electricity versus gas. Is that true? All right, well, we'll go into some of the studies here. So this is a study, I don't know if Nick Brown was able to make it today, but he did various modeling studies looking at performance, 3 different climate zones, comparing 4 different replacement scenarios versus just a like for like, changing out today's best standard gas furnace technology versus changing it out to central heat pump, ducted mini split, ductless mini split, or combination window AC with a wall furnace being changed out to ductless mini split. So you can see that in all but one of the mountain climates, there is a positive impact from changing to an heat pump system versus a gas system. So even though on a unit basis, electricity may be more expensive, particularly depending on when you use it on a time of use rate, your efficiency gains, because a heat pump is so much more efficient, the total cost of your energy bill is projected in most cases to be lower. And you can see it varies depending on the type of system. And of course, this is a average 1996 to 2012 vintage home. And there's so many more factors that go into what your actual energy bills are going to be, how your envelope performs, what your specific microclimate is, all of that. So you take these numbers with a grain of salt, obviously, but all other things being equal, looking at those various factors and studying a prototypical home, comparing it to the replacement scenarios listed here, there's a positive benefit in nearly all of those cases. And I don't know if Nick is on the line and had anything to add, having been the author of this study or not.
I'm
give him
here.
a second
Thanks
to
for the shout out, Dave.
Yeah.
I would just add that it seems like the biggest cost savings are in HVAC with electrification, with water heating and cooking and laundry more of a push, more of an roughly the same utility costs when we did this run.
Great, and that's a great point, Nick. Yeah, and part of that stems from just less hours of usage. We just don't use our stoves, our cooktops all that much compared to, in the heating season, we use our heaters a lot. And, climate zone's gonna matter. In some climate zones, heating is going to be, and space conditioning is gonna be your driver. And in some climate zones, it's very mild and you have you're coastal, you don't have a huge heat load, and so water heating is going to dominate, and we see that maybe more on the Central Coast, for instance. So your mileage may vary, but generally speaking, HVAC savings can be very significant. And this is only going to increase in terms of the savings margins over time. The CPUC has done studies to forecast what the various energy rates are going to be over time in terms of the cost escalation. Because there's so much electrification forecast on the grid, what's projected is that you'll have more usage spread out over more or less the same infrastructure, which is going to bring down individual rates, or at least ease cost escalation pressure, so that the rates increase at a much slower rate. Whereas as more and more customers switch over from the gas system, but you still have that fixed infrastructure, you're going to have stranded assets that need to have costs that need to be recouped over a shrinking customer base, and that's going to drive individual rates up higher and faster than what the electric rates are projected to be. So it's a gap and a divide that's forecast to increase over time in terms of the cost benefits of electric versus gas. In terms of electric vehicles, a great way to compare is to go to cars.sce.com, and there's a great calculator on there. This is a screenshot of it that will allow you to say, okay, I'm considering this class of vehicle, whatever. This is probably a small SUV class. You can do kind of larger trucks, you can do compacts, etc. And you can compare what based on their fuel efficiency, what your vehicle that you're considering purchasing versus the standard similar gas vehicle, and what it would cost based on kind of average miles driven, average cost of electricity, average cost of gas. And there's some sliders so you can see based on what you might be paying, or gas prices go up and down. These numbers will change a little bit, but you can use the calculator to do that analysis. But based on, I think this was $4.50 per gallon, and current electric rates on average, someone with this kind of mid-range class of vehicle would save over $200 a month in fuel costs if they're doing kind of a standard commute a few days a week. Additionally, and what this doesn't capture is some of the life cycle cost savings as well, which is that EVs have significantly fewer moving parts than internal combustion vehicles, so you don't need things like oil changes regularly. You don't need as many tune-ups, so you see a lot of savings on ongoing maintenance there as well. And I'm sure if there are folks on this call who drive EVs, they can probably share some stories maybe in the chat as to what they've seen as well. All right, I don't know if there were any additional questions in that section, or I can go on to kind of first costs.
No additional questions as of now.
Great. So we also get a lot of questions about what about upfront costs? You're putting in this electric infrastructure. What about these appliances? They're not necessarily as readily available because we're in the midst of this transition. Doesn't that drive costs up? Contractors not being as familiar with some of the technologies, et cetera. Fact or fiction? Well, starting with new construction, a lot of growing body of evidence is showing fairly conclusively that the upfront savings from building all electric and avoiding the gas infrastructure and piping and all the different connections within your house saves $7,500 to $8,200 to build all electric. That was from a cost study of the Building Decarbonization Code that New Buildings Institute published in 2022. This was based on nationwide data across 4 different municipal areas that they looked at in terms of prevailing costs and labor and all that. What I would give this an additional bump in California is that since this study was done, of course, the latest energy code has gone into effect here, which requires all projects to put in electrification readiness. So the delta between a mixed fuel and an all electric building are now going to be that much greater because you already have to factor in the costs of some of those electrification upgrades, the additional circuits, probably still putting in the same size panel, ideally, 200 amp panel in new construction anyway. But that is now pretty much factored in. So that adds an additional few $1,000s to that estimate. If you consider that that's now in the mixed fuel baseline as well. Additionally, a study in 2019 from Energy and Environmental Economics, E3, the kind of broad look at residential building electrification in California. They compared capital costs per unit of all appliances and infrastructure, including the gas connection costs for new construction, and they found savings for all electric in all but low-rise multifamily in climate zone 3 in San Francisco, and that was almost a push in that case. But otherwise, pretty much, savings, varying amounts for going all electric in each of those climate zones.
Hey, Dave, we have a question in chat. What size panel were you referencing?
The electric panel. So the minimum code panel is going to be 200 amp panel for residential.
Okay, thank you.
Yeah. Now, retrofit gets a little bit more complicated because you have quite a variety of different existing conditions. So your costs there are going to be driven by a lot of different factors. And of course, in most cases, you're going to already have the gas infrastructure in place as a sunk cost. So that's going to potentially change your cost analysis. So it's hard to throw any kind of a ballpark figure or average figure at what's going to be the cost of a retrofit. You're really going to need to kind of evaluate that case by case. Some of the different factors that will impact that. What's the available space for the equipment? Can you just drop in, the new heat pump water heater? It's got a slightly bigger form factor. So will it fit in the existing space? If you have a tankless, that could complicate things even more. Unless you have a garage, you can put the unit in. So multifamily versus single family, you're going to have different challenges, right? Are any of those features going to trigger electrical system upgrades? And we'll talk a little bit about that in a moment, with some of those considerations. How ready is the contractor pool to help you through this journey? What's the timing? Are you trying to replace during an emergency situation where you've had an equipment failure and you don't have the available outlet and infrastructure, and you need to engage both an electrician and a plumber because your water heater failed, and now your family is like, okay, I need to take hot showers, let's get this done, right? So that's going to affect how much it costs if you're in an emergency situation. The specific equipment you select and what features it has. How far do you need to run new circuits? Are you close by, as in this photo? Well, you know, that's an easy, you know, you're only going a couple of feet versus if the garage is 50 feet away, that's a different, you know, it's a lot more conduit and wire to run. And then finally, you know, what's the remaining useful life of your replaced equipment may be a factor as well.
Hey,
I wanted to
Dave,
direct, yeah,
I wanted to step back to the electrical panel, although I see you're kind of coming up on that now.
yeah,
There was a
sure.
follow-up question. Is a 200 amp panel enough for an all electric house?
In virtually all cases, yes. You know, the exceptions will be things like, do you have, you know, pool pump, spa pump, an ADU that's also powered off of your main panel. So when you start to add in those kinds of things, you know, you really do need to look closely at what the calculations are and if you're going to have adequate service. For the majority of end uses, the majority of homes, you know, I mean, if your house is, you know, that the median size or less, or even, you know, bigger, you're really going to be, you're going to have to do a load calc. The bigger your home gets and the more kind of non-standard loads you have on the house. But you know, we'll talk a little bit about kind of loading and panel sizing when we get to kind of the can the grid handle this piece, which is coming up, I think, after this section. But the short answer is, in almost all cases, yes.
Okay,
So,
thank you.
yeah. So in those cases where you know, you would like to avoid the cost of a panel upgrade, there are strategies and technologies, including load sharing devices, 120 volt appliances, heat pump water heaters that don't have the backup electric resistance element are now on the market and can plug into a shared circuit, 120 volt, and provide adequate water heater or hot water based on, you know, considering if you have a really large family that takes a lot of showers, maybe you really need to look closely at that. But for the bulk of conditions, most of the time that's going to be adequate to meet your needs. And you know, the load sharing devices are key. In some cases, you can instead of having dedicated circuits for things like you know, your stove, your water heater, your electric vehicle charger, you can have a device that allows multiple devices, typically two, to plug in and to be able to share a circuit, and it will have a priority. So if you go to charge your car, then it might pause your water heater and vice versa, you know, depending on how you set the priority. So you can have multiple devices plugged into the same circuit, but it will control so that it doesn't operate both of them at the same time. So therefore, it's reducing your potential peak load. And then, of course, improving your overall envelope efficiency is going to reduce the amount that your HVAC system needs to run. So a smaller HVAC system is obviously going to have a smaller draw. So all of those things are tied together: efficiency, on-site generation, battery storage. You know, battery storage can help, especially if you integrate that with a smart panel in terms of managing your loads and how everything flows. So that's a downloadable resource from the Redwood Energy website. So if you're trying to do electrification and stay within an existing 100 amp panel, I definitely recommend you check out that resource. Speaking of resources, there are incentive programs available. I'm not going to go into a lot of detail in it here because we have a lot to cover, and I want to get to some of the other topics. But just understand that for new construction, there's the California Energy Smart Homes program. There's the BUILD program, the Building Initiative for Low Emissions Development, run by the CEC. Those address new construction. And for retrofits, there's the Tech Clean California, which will provide incentives through the contractor that reduces the cost of your installation for heat pump water heaters as well as heat pump HVAC. Additionally, There's federal incentives and tax credits, very generous program enacted through the Inflation Reduction Act. There's a great calculator. I don't know if I have a link to it at the end, but basically Rewiring America has a really helpful calculator where you can plug in your zip code, your income, and I think those are the two main variables. And then it'll list out all the different programs and rebates that you'll qualify for. The tax credits are available now. The point of sale rebates are coming very soon. The DOE just released the guidance on those for states, and so California will be adopting those rebates probably within the next 4 to 6 months, but we'll see exactly when it happens. All right. So what about power outages? That's a big concern with people. They are concerned about resilience and they want to use gas appliances if their power is out. Is that realistic? Well, just a note about outages. We recognize they're inconvenient, very impactful to customers, but they are relatively infrequent. Certainly, when we have a hurricane or a tropical storm come through, there's going to be a little bit more chance of that happening to customers. However, the last 5 years, all of the utilities have made significant progress in grid hardening efforts that are reducing the amount of public safety power outages that need to take place as we are addressing the increased incidence of extreme weather events and how our grid responds to that. So we've seen a significant reduction in those outages over the course of the last 5 years as we've provided a significant amount of grid upgrades. In fact, the impact of PSPS outages has been reduced by 80% since the 2017-2018 cycle. On average, a typical SCE customer experiences 1 outage per year for a duration of about 2 hours. Now, if you're closer to the wildland urban interface, where the grid, kind of got more vegetation, got more exposure to potential hazards and winds and things, that's might be higher. If you're in a very urban area, it potentially may be lower. Outages realistically cannot ever fully be avoided. From the standpoint for any utility system, you're going to have certain outages and disruptions of service just to maintain and provide upgrades to the services. But efforts are made to isolate the outage areas and reduce impacts to affected customers. And of course, we have question.
And sorry to interrupt there. I thought you were finishing. I wanted to catch you.
That's good. Yep.
Couple things in chat. One individual posted a link to rewiringamerica.org.
Oh, great.
IRA
That's excellent.
calculator.
Mm-hmm. That's the one. Thank you.
Good. So people, you can find that in chat. It's kind of, you only have to scroll a little ways up to see it. And then there was a question on Sharish. I'm not sure if you want to go ahead and state yours, that's fine. Unless you have battery storage, but there is one Sharish put in there that is PUC allows grid shutdowns during fire. It's a question.
Yeah, so that's what I was referring to in the public safety power shutoff. That went into effect, that protocol went into effect about 5 years ago. And as I noted that, there significant efforts, we've put in tens of thousands of lineal miles of covered conductor. We've put in composite power poles. So we're doing the kinds of things to basically increase the thresholds where that type of a disruption would have to occur. And again, the impact of those outages has been reduced by 80% in terms of the number and the duration of those outages in that time. And it keeps going down because we keep focusing on the most vulnerable circuits with those upgrades. So it's definitely been disruptive but it's something that the grid continues to work on upgrades to improve the performance in that regard. So a couple of notes about what if there is an outage? The reality is that nearly all modern gas appliances have electronic ignition or controls, so you either can't or shouldn't be using them if they don't have power to them. Some of the health impacts that have been recently kind of more and more made aware through folks like the American Medical Association, Sierra Club, American Lung Association have identified significant increases in asthma risk from the presence of gas stoves in homes, and that the code itself has, as you may recall from the recent code breakers that Nick has led, requires higher ventilation as a result of this knowledge for if you install a gas appliance versus an electric cooktop. So you really shouldn't be cooking indoors with gas if you don't have ventilation. If you have a grill, you wouldn't roll that inside and cook with it. But if you have a grill, you may be able to just, boil water on that or cook on that. Or there's some, plug-in units you can put into a battery that you could use if necessary. So there's kind of considerations there as far as cooking, right? If you have a brief outage. And similarly, folks worry about charging an electric vehicle if the power goes out, but gas pumps also need electricity to operate. So if you're in an outage area, if you're in an outage area where you have to drive to get gas, then if they're out too, you wouldn't be able to fuel. If they're not, then presumably you could drive to a public charger to charge your vehicle if you needed to. So those are all considerations as well, is that, having a mixed fuel home maybe doesn't give you the kind of resilience you might think. Now, one thing that the code is putting into place to help with resilience as well as kind of grid interactivity is a requirement in residential for battery readiness. And of course, as we know from our non-residential code breaker classes, that you actually have to provide these systems in multifamily construction as well as commercial construction, most occupancies. So this diagram should look familiar from our code breakers in terms of having that sub panel with critical loads, space provided for a battery. And if you actually install a battery, then you'll have that resilience. And if it's paired with solar, that's going to be something that can renew day after day, and you'll be able to ride out potentially long outages, right? That can serve your basic needs. So that's something to consider and something that's been worked into the code.
Hey, Dave,
just one,
there is a question here.
Sure.
I wanted to sneak it in there because it deals with solar. Can you
Absolutely
tell us why you think the tax credit isn't much higher for installing solar?
The tax credit itself. So the IRA tax credit, I think, is 30% of the installed cost. Don't quote me on that, but that's my recollection. Same thing with a battery system. I can't say why they set them as they do, but I think historically that's been about the level that it's been at. And I don't know, Nick, if you have any other insights onto the tax credit piece of solar. I know you deal with that a bit, but it's pretty generous overall. A third of the system covered by a tax credit.
And I see a confirmed solar tax credit is 30%.
Okay, great. Of course, you have to have enough tax liability to take advantage of that. But if you're buying a system outright, chances are you're doing pretty well, and you've got some income that you can, apply that toward. Okay, so I just wanted to talk a little bit about the potential for EVs, and there's another slide coming up that we'll get to that will elaborate on this a little bit more. But I met a contractor who's the executive director for National Home Building Energy Efficiency Group, EBA. He has a Ford F-150 Lightning. They had an outage in their area, and he ran extension cords to a couple of houses. He rolled his vehicle into his backyard, plugged in his fridge, freezer, his neighbor's fridge and freezer, exotic fish aquarium, internet router, electronic devices, so the kids could keep playing their video games, you know, while the world was coming to an end. After 6 hours of running all of those loads for multiple houses, his EV battery was down 5% from where it started. The equivalent on these long range trucks, pickup trucks, is roughly the equivalent of 4 or 5 power walls. So it's a significant amount of, you know, basically this mobile battery that you happen to have in your garage that, you know, can be leveraged as a resiliency asset. We'll talk a little bit about the potential for vehicle to building technology that will allow you to use your charger as a plug into your house and allow the house to draw power off of your vehicle, whether for resiliency or potentially to reduce your peak demand. So we'll talk a little bit about that in a little bit more detail. I got another slide coming up on that, but just an interesting anecdote about how useful that was in that situation. Okay, what about the raw materials it takes for PV panels and batteries? They're energy intensive, they're mineral intensive. Doesn't that wipe out their environmental benefits? Is this all for naught? Fact or fiction? So the Intergovernmental Panel on Climate Change has taken a look at this, the IPCC. They demonstrate that the life cycle emissions for PV are 12 times lower than natural gas and 20 times lower than coal on a life cycle basis. So you do have that upfront manufacturing emissions in terms of putting that system in place and getting the raw materials, but because it's carbon-free electricity from that point forward over the life of that system, you know, which is projected for decades, it's, you know, 12 to 20 times better on a life cycle basis. On the electric vehicle side, again, that life cycle benefit is going to vary based on how clean your grid is. That's what that kind of thin line is on these graphs. But if you compare a battery electric vehicle to the internal combustion vehicle, that yellow bar is the emissions impact from all of the fuel used over the life of that vehicle. So you have a slightly larger, though not huge, increase in embodied carbon emissions up front, but you save so much in terms of emissions over the life of the use of that vehicle that it, you know, more than makes up for that by a factor of at least 2. And if you're in a state like California that's moving towards carbon neutrality, or if you have a solar array on your house and you're already effectively at 0 carbon now, because you're charging your car and running your house off of 100% solar, clean energy, then that increases that benefit on a life cycle even more. Any questions there on either of those? All right, what about how established are heat pumps? Aren't they an unproven technology with a small market share? Well, heat pumps have been around since their invention in 1856. You've had one in your house your whole life. Your refrigerator runs on this principle. It's just not reversible. You can't heat the food inside the box. You can only cool it. But it's the same idea. Compressor runs that refrigerant loop, moves heat from one place to another. Heat pump technology just gives you that reversing valve that lets you both heat and cool.
Hey, Dave?
Heat pump, yes, question.
Sorry, I couldn't get off mute quick enough before you moved to this section. There's a question, do we have a way to recycle PV panels? What do we do when the panel is spent?
Yeah, so that's a good question. I don't have the stats on that, but I know that infrastructure is in place for that recycling, and batteries in particular. So there's companies that are looking at removing, because typically with an EV battery, which effectively is designed for the life of the vehicle, nearly all batteries that are manufactured in EV cars, and this is going back, you know, over a decade in terms of, you know, early Teslas and Nissan Leafs and et cetera, are still in service in those vehicles. So at the end of life, typically end of life is considered when you get to 60% or lower of your original output. Those batteries still have capacity, and they're looking at ways to actually take those batteries and utilize them in storage arrays that would be used at the utility scale. So you would have them as a feedstock for another process that would allow continued usage outside of that vehicle. Okay, so just wanted to point out that for the first time in 2022, heat pump sales exceeded gas furnace sales in 2022. And this is sales data directly from AHRI, the Air Conditioning, Heating, Refrigeration Institute that tracks the industry. They're very common in the Southeast. I think heat pumps are over 40% in states like North Carolina and Florida. And Asia and Europe, of course, have had heat pumps for a very long time. And of course, as you know, this graph should be familiar. They're now the prescriptive minimum standard in various climate, or every climate zone. It's just whether you have a heat pump water heater or a heat pump space conditioning system as your prescriptive baseline in your Title 24 compliance. All right, then what about the idea that heat pumps only work in mild climates? They can't handle when it gets cold outside. I've had contractors tell me, oh, if it gets below 40, your heat pump's not gonna work. Is that true? Was it true at one point? Maybe it's not true anymore. So I just wanted to share this snippet. This is just from just a few weeks ago. Maine announced that it's sold heat pumps so fast that they blew past their 100,000 heat pump target that they had set for 2025 about 18 months early. So now they're pledging to almost triple that target by 2027. There are heat pump systems specifically designed for cold weather that can perform in temperatures as low as -13 degrees Fahrenheit without an electric resistance backup. So keep in mind, even when it feels cold to us, there's still heat in the air to be removed. And specifying the right equipment for the right climatic conditions is really critical. That's if you put in the wrong heat pump that won't work, or not, it doesn't have the systems designed to optimize for the right conditions, that's where you could run into problems. So working with an engineer to make sure that that's the right system for your home, working with a qualified installer that understands the equipment, that's a really critical formula for success. Couple of quick notes on electric stove. We're getting close on time, so I don't want to kind of run over too much. The advancement in electric technology, we talked a bit about induction. The key things are greater precision and control, enhanced safety. You'll see demos where they have like a magazine or a towel underneath the pan on top of the cooking surface and no problems. Super easy to clean. You just wipe them down when you're done. Better air quality because you don't have the byproducts of combustion, putting asthmagens and carcinogens into the air, and exceptional energy efficiency. Surface remains cool to the touch, adjacent to the pan while cooking. Consumer Reports in 2020, 6 of their 8 top rated stoves were electric. The top 2 were induction, and you can see based on the cost that they're not significantly more expensive. In fact, in many cases, they're cheaper than the premier gas stoves that also rated well in that study. And if you think about it, we already do a ton of electric cooking already. Even if you have a gas stove, you're using your toaster oven, you're using your air fryer, crock pot, sous vide, waffle maker, etc. So it's just continuing that trend. All right, so I have a lot of graphs in this section. I'm going to kind of blow through it a little bit, but basically the idea that the grid can't handle this load. What about the flex alerts? They're telling us to conserve our power. Can the grid handle this new load? So I want to just point out that as we make this transition to cleaner power, renewables that are available at different times and cause different peaks and different supply curves, we're putting a lot of things in place to address those challenges. We understand that we're going to need a lot of distributed energy resources on the customer side that we're going to have to, interact with on the grid side. We need to make sure that there's adequate resources. We need to ensure that our grid assets are performing and resilient in the face of extreme weather, and that we have policies in place that ensure that as we make this transition, there's an equitable access to these technologies for all customers. We have a vision of how this is going to be achieved. There will be enhanced planning and software tools to ensure real-time management of how these different grid operation systems and interactions with customer side resources are managed, leveraging resources like battery storage, automation, understanding the regional needs of the grid, being more proactive about putting the right resources at the right parts of the grid so that as customers are making the transition, the resources are there to support them. Couple of quick points on how all electric homes, they do have a higher usage and a slightly higher peak than hybrid homes, but it's moderate, right? So Sacramento Municipal Utility District did a study of about 100,000 homes, looking at their mixed use homes or mixed fuel homes compared to their all electric homes. And they didn't see a significant increase in the peak amperage. So you'll notice that even the highest demand homes in terms of their 1 hour peak, none of them exceeded 80 amps. So this comes from the fact that most of these end uses have a high diversity factor, meaning that they're not all on at full power at the same time. That gives you a lot of kind of flexibility and capacity in kind of your electrical distribution system. They're not operating all the time. They're intermittent. You're cooking only during certain hours. Your water heater is operating only during certain hours. And most of the time, if you have a heat pump water heater, it's operating in heat pump mode, which is very efficient. It's equivalent to having a second refrigerator in your garage. It's only when that electric resistance element in a hybrid water heater kicks on that you have that kind of power spike. But that's a very, very intermittent type of incident. Similar study in homes in SCE territory showed that yes, they use more power. Understandably, they have more electric appliances, but that usage is spread out more during the day. The peaks did not significantly increase, only slightly compared to mixed fuel homes. And these graphs kind of show in the blue that all electric home and the difference in usage being kind of moderate relative to the hybrid home. So we are getting close here. I have a few more slides. So if anyone has to drop, I appreciate that. I'll just cover this in the last few minutes here if you bear with me. So quick, I'm sure many of you have heard of the duck curve. As we've had more and more renewables come onto the system, and you can see how the projections and actual curves of supply on the grid have borne out. But we see this, what they call the belly of the duck, where there's more and more solar production providing a dip in actual needed demand that the grid needs to supply. But then that transition that ramps up in the evening hours, 4 to 9 p.m. primarily being the area of concern. And that is where we potentially have those flex alerts on the hottest days. And that's usually when there's a flex alert, it's just asking customers to conserve or shift usage during that 4 to 9 p.m. period primarily. So you still have those shoulder hours or those hours outside that when, if you need to charge your electric vehicle, that would be the optimal time to do it. If you need to do laundry, that's the optimal time. So we're looking for customers to modify behavior during those areas when the grid is most stressed so that they can be part of helping to keep the infrastructure needs that are driven by that peak demand down, which helps to reduce the overall cost of delivery. A major factor that's helping to mitigate that neck of the duck is the deployment of battery storage. The long shot is that at this point in summer of 2023, we've gone in the last roughly 3 years from virtually no battery storage, roughly 175 megawatts of grid-side battery storage, to 5,600 megawatts of battery storage connected statewide to the CAISO system. So that's like a 25 or 30-fold increase overall. And to put that in perspective, Diablo Canyon is the largest single generator in the state, 2.2 gigawatts. So this is almost like 2.5 Diablo Canyons that we've had just in deployable utility scale battery storage. And you can see here that blue line, that's that kind of battery capacity back in 2019, give or take. The dashed yellow line is how much new renewables have come on in that time. And the red line is the deployment of battery since then. That's in 2023, March 2023. So you can see battery deployments have roughly coincided with the addition of solar in that period. So it's helping to shift that overproduction of solar during the day to those evening hours. And you roughly can see that that follows that curve you saw on the duck curve. So one last slide here, and then just a couple of slides of resources to leave you with. And again, thanks for sticking with me, those that have. Just a note, coming back to that idea of how electric vehicles have a potential to become grid assets. Just in terms of the number of vehicles, electric vehicles that we have in ownership in California today, it's nearly 1 million, give or take. This will obviously grow over time. We were in the most recent quarter of sales, 25% of vehicle sales statewide were electric vehicles. That's up from 20% the previous quarter. So we're seeing that kind of exponential adoption. If you assume 37 miles of daily use and maintaining 80 miles of reserve range, that still leaves roughly 37 gigawatt hours of vehicle battery that would remain for grid use, where you could deploy that during that peak on those most constrained days. If you have this vehicle to grid or vehicle to building capability, which some of the OEMs already have, and we're just seeing how that's going to be deployed in terms of policy. But this is an emerging area where the potential for vehicles to provide grid resiliency benefits, and for customers to benefit from that, and to potentially, see reduced rates or to be paid to do that. That's something to watch for, and something that's going to come. And you're going to be buying that car anyway, so it's an asset you have access to. So just something on the horizon that is going to be part of the solution. When people ask, aren't these EVs going to be a problem? I always think of them as really a big part of the solution. Okay, so a couple of resources: switcheson.org. This will help you navigate that transition to electric. A lot of great resources. Find a contractor. If you're a contractor or know a contractor that's interested in how they kind of take advantage of being an installer and take advantage of those incentives, they have a portal there for them as well. We have a new recently released book of case studies on multifamily all electric buildings that can be downloaded from the internet for free, viewed as a flip book, and you can buy hard copy at cost on Amazon as well. Great volume looking at 5 case studies of varying types of multifamily construction, all electric built in California. And then finally, of course, you're very familiar at this point with Energy Code ACE, instructors like Nick running training, and then all the tools and resources we have to support you there. So again, sorry to have gone over time a little bit. Thank you for those that kind of stuck with the whole way. And if there are any final questions before we close out, I'm more than happy to take those.
There are a couple. One of them is, will the PDFs of this presentation be available for attendees?
Yeah, I'll send that over, and that can be distributed to attendees, no problem.
Okay, and then the next one is, how successful is Tesla / SCE virtual power plant?
Yeah, so I'm not sure if we have any pilots on virtual power plants yet. I know there are a number of utilities that have done that. There's been a great case study in Utah. I was just reading about one in Vermont. So again, that's going to be, I think, whether it's stationary batteries or vehicle batteries plugged in and functioning the same way, we're going to see more and more of that, because having kind of mass access to that type of a resource to call upon, you could see from the graph there, even after you consider the daily commute mileage and reserve mileage you would want to keep, there's more EV capacity that could potentially be available than we currently have grid battery. Any other questions, or is that it?
Let me see. No, I believe that is it. If anybody wants to ask a question, please feel free to go ahead and come off mute.
There was a comment, I can see the comments now. Somebody said something was ugly on the side of the house. I don't know which slide it was referring to, though.
I think it was the one of the home, maybe in Maine.
Oh, okay, right, yeah. Yeah,
I'll go ahead and shoot. I do have a really
yeah.
good question. I'm on the
Okay.
building side, also the design side.
Mhm.
But 200 amp panel is pretty small, you know, but when you factor in all the new demands for you know, appliances and you know, just everything that's going into a house, it seems like relatively like small amp panels, and I'm seeing more like 400 amps, like, you know, for more of the maybe larger size homes. And I'm just wondering, is that like something that's probably more realistic than going with like a 200 amp like standard service for a small house?
Well, like you said, it's going to depend on what the loads are. If it's a larger home, that may be something that your engineer is going to recommend. Most kind of average size production homes are going to be perfectly adequate with that. Again, most of these loads are fairly intermittent. The heat pump water heater, for example, you know, we talked about, it's not going to be running in electric resistance mode most of the time. So even though you might have a 30 amp circuit, you know, it's only pulling, you know, a fraction of those amps when it's actually operating, which is maybe 2 to 4 hours a day. So again, it's kind of up to your electrical engineer to do that sizing.
Right.
But a lot of
that's what I'm asking is
yeah.
so, but typically you're talking about production now, you're talking about like more like track homes, not like, you know, basically like one-off design, you know, production for like architecture. But I mean, production house, I was in production housing for 30 years, and I'm like, yeah, that's fine for a track house. But
Yeah.
I mean, most people are not hiring architects to build track housing, you know, so that's why I'm wondering, like, you know.
Well, the multifamily, I mean,
Okay.
those units, right? Yeah.
Yeah.
So yeah, again, you know, you need, if you're going to have a large variety of high draw appliances and equipment, you know, you've got, again, pool pump, pool heater, spa, multiple electric vehicle chargers, an ADU or guest house. I mean,
Right.
all of those things are going to drive larger panel sizes, right?
Is that like, is that, and you're saying that though, that the grid should be ready for that kind of like upgrade or increase in demand?
Well, just because you have that panel capacity doesn't mean you're drawing it. And I would refer
Right.
you back to the graphs I showed that it's more usage, but it's spread out over the day. I mean,
Right.
think about if you're designing a freeway, and you can get everyone to drive at different hours, you
Right, it's
can
fine.
get by with fewer lanes.
Yeah.
You know, you don't have to have, like, assume everyone is driving the car there,
Right.
you know, at the same time. If you're assuming in your electrical design that heat pump space heating is doing, you know, maximum, you know, it's a super cold winter day, you're heating in resistance mode, you're charging your vehicles at all the time, you're boiling 8 pots of water. If
Yeah.
all those things are on and you're heating your pool and all that, yeah, you probably need a big panel. But how
Right.
often are those end uses going to be coincident?
Okay. So we're basically being able to like shoot for, you know, well, like I said, probably about me. You're saying 200. I'm gonna try to see if I can figure that out. But
Well,
I'm typically designing by
I mean, that's the average house, right? You're talking
Yeah.
about, you know, houses that are not average, and
Right.
those you're going to need to engineer for sure. No question. You can't just blanket, you know, stamp it like, okay, here, 200 amp, we're good to go, right?
Right. Okay. Thank you so much.
Yeah, of course.